function notation, we've also spent a little bit of additional time working on domain and range of functions themselves. Today we're going to do some things with function arithmetic. We're going to add, we're going to subtract, divide, and multiply functions, utilizing Desmos or a graphing calculator to help verify the domain of these. And then we'll end our time talking about the difference quotient. So let's suppose that f and g are functions and x is some kind of element common in the domain of both of those, f and g. We can ideally add functions together and subtract functions together. If f is the domain of function f and g, then the domain of, if I'm adding or subtracting the function, is the intersections of those two domains themselves, f intersect g, which means where the domains overlap. So let's look at our first example. Let's have the function the square root of x plus 3 and 2x minus 1. So we've got a square root function and we have a linear function. When I'm thinking about x plus 3 and the square root of it, we know that items underneath the square root need to stay positive. So let's first, before we do anything else, look at the domain of each individual function itself. When I'm looking at the square root of x plus 3, its particular domain needs to be greater than or equal to 0, because we know that square root functions, they can't have negative numbers underneath. So we're going to set it so that it's greater than or equal to 0. And then as I solve, x will have to be greater than or equal to 3. So therefore, my domain for the square root of x plus 3 starts at negative 3 and it goes to positive infinity. However, when I look at the domain of 2x minus 1, I know that this is a linear function, and a linear function expands in both directions forever and ever. So all linear functions have a domain of negative infinity to positive infinity. So where do these two overlap? Well, they're going to be overlapping at this particular place, from negative 3 to positive infinity. That's where they are on top of each other. So we can also look at adding our functions together. So let's add our functions together and then verify this using a picture. So ideally, all this is doing is taking the f function of the square root of x plus 3 and adding it to my g function, 2x minus 1. There's nothing we can do to simplify. They're not equivalent together. I know it looks kind of messy and ugly, but it is what it is. So when I'm looking at the picture of the addition of these two together, I took a screenshot of Desmos and brought it in. I see that the farthest left that my graph goes is at negative 3, and my graph is continuing in the positive direction forever and ever. Right, because we're going up and to the right forever and ever. So therefore, where our graph is overlapping is from negative infinity to positive infinity, the overlapping of negative 3 included to positive infinity. And another way you could look at this is, if I think of a number line, negative infinity to positive infinity would be all the way on the top, right? We go left and right forever and ever. However, negative 3 to positive infinity would start at negative 3 included and go towards positive infinity. So it's this area in which they are overlapping or on top of each other. So that's another visual way to look at it. Next example is use the same function to once again add, but now we need to evaluate at positive 2. To do this, we already have our function set up, so I know that f plus g of x is equal to the square root of x plus 3 plus 2x minus 1. Now I want to evaluate. Wherever I see x, I'm going to replace that with 2 and simplify. So I'll have the square root of 2 plus 3 plus 2 times 2 minus 1, or the square root of 5 plus 4 minus 1, which reduces to the square root of 5 plus 3. And this is its exact form. Be careful with my open math if it needs the exact form or a decimal, whatever works, whatever it's asking us to do. This next example we are going to take the same functions that we had on the previous slide, and we're going to subtract them and evaluate at 6. So we can do a couple of these steps together. So I want to take my functions and I want to subtract them first, and then we'll evaluate at 6. So I want to take my f function, the square root of x plus 3, and I want to subtract the entirety of function g. So I want to subtract all of 2x minus 1. So I will need to distribute. Be very careful with subtraction. This is where a lot of things can go wrong if we're not careful with subtraction. So this becomes minus 2x plus 1. We can now easily evaluate this for 6. So I'll replace this and put 6 in. So wherever we see x, we're going to substitute it with 6. So the square root of 6 plus 3 minus 2 times 6 plus 1 is the square root of 9 minus 12 plus 1, or 3 minus 12 plus 1, which is negative 8. Notice here that even though I'm subtracting, my domain still remains the same from the previous page. The domain of the square root of x plus 3 we stated on the previous page was negative 3 to positive infinity. And the domain of our linear line was negative infinity to positive infinity. And where they overlapped together with their subtraction, the domain of f minus g of x, its domain will also be their overlapping of negative 3 to infinity. I see this is true with my graph. I copied the graph from Desmos, took a screenshot to bring it in. I look like I'm going by pairs of 2 since I'm at 2, 4, 6, 8, 10. So negative 3 would be here. I am included here, and my graph is moving to the positive direction forever and ever. Also, I see we've got a new function. This time I'm pairing together x squared minus x. So I've got two different quadratics that I'd like to subtract, and then I would like to evaluate at negative 1. So I want to take f of x and subtract g of x. So notice I'm just doing a little bit different function notation. Instead of putting them in one parenthesis, I'm kind of putting them in 2. This is the same thing then as saying I want to take x squared minus x and subtract 12 minus x squared. So notice I'm putting the parentheses around 12 minus x squared to ensure that I'm subtracting everything from g of x. Then I'll distribute, so I'll have x squared minus x minus 12 plus x squared. I can also combine like terms, so 2x squared minus x minus 12. Now I want to evaluate this at negative 1. So f minus g of negative 1. So wherever I see x squared, or x, I'm going to replace with negative 1. So 2 times negative 1 squared minus a negative 1 minus 12. Negative 1 squared is 1, so 2 times 1 is 1. Plus 1 minus 12, therefore we are at negative 9. Notice in Desmos, taking a screenshot, I have the subtraction. If I think about a quadratic equation, a quadratic is going to the left and to the right, either up and out or down and out, forever and ever. So the domain of my f function for a quadratic is negative infinity to positive infinity. For my g function, I also have a quadratic. It's just an upside down quadratic, but it's still going to go from negative infinity to positive infinity if I were to graph them independently. So it shouldn't surprise us that negative infinity to positive infinity is in fact the domain of this subtracted function. So if I look at my graphs are going to be going up and to the left and to the right and to the left forever and ever. So therefore, the domain of f minus g of x is in fact negative infinity to positive infinity. We also are able to multiply functions together. We can multiply functions together doing the same technique of adding and subtracting, simply taking our functions and multiplying them together. The domains then is still the overlap, so it's still the overlap. So we're going to follow the same strategy that we did for adding and subtracting. It's where they're intersecting one another. We have the same functions with which we started with, the square root of x plus 3 and our 2x minus 1. Here we said the domain was from negative 3 included to positive infinity, and the domain of g of x, we said, because it's a linear line, is from negative infinity to positive infinity. So its overlap, so f times g of x, its domain will be the overlap, so the same as the adding of them, from negative 3 to positive infinity. So what is f times g of x? I'm going to take my f function, square root of x plus 3, and multiply it by my g function and see if I can simplify. I certainly could multiply and reduce some of these parentheses, but not always needed. We would then have 2x times the square root of x plus 3 minus the square root of x plus 3. They equally look complicated, so you can leave it like this unless it were to simplify and reduce down. When I graph the square root of x plus 3 times 2x minus 1, using decimals, I took the screenshot. When I'm looking at how far left and right, I do see my graph, the far left, as far left as I'm going is negative 3, and then I'm going all the way to positive infinity, since this part of the graph is going up and to the right forever and ever. So just as we had stated, our domain will be negative 3 included to positive infinity. Well, now that we have the functions multiplied, it's asking us to evaluate at positive 1. Well, now that I have it listed here, I could easily take f times g of 1 and substitute 1 and 2 wherever I see x and simplify. This gives me the square root of 4. 2 minus 1 is 1, so this gives me 2. Using the same functions, let's also find f of g of negative 1. Again, everywhere I see x, I'm going to replace it with negative 1. So the square roots of negative 1 plus 3 times 2 times negative 1 minus 1. This gives us the square root of 2, which is not a nice number, times negative 2 minus 1, negative 3. So its reduced form is negative 3 square roots 2. Again, be careful with what my open math wants. Does it want it an exact value, or is a rounded decimal okay? Now as we work towards the division, we have a couple things we need to be aware of. So we can certainly take the division of our functions as long as the denominator does not equal 0. We know that if a denominator, a function is equal to 0 when we divide by 0, it does not exist. It's not possible to do so. And we also have the intersection of the two domains. So just as if we were doing the domains beforehand, we'll want to take into consideration also not only where they intersect, but also and where does g of x not equal 0. So we have a little extra piece. So not only is it the intersection, but it is also where g of x does not equal 0. Let's take a look at that. We have our same function, square roots x plus 3 and 2x minus 1. Before we evaluate it at positive 1, let's take a look at what the simplified version is, talk about the domain, and then actually go forth and do that. So when I'm looking at f divided by g of x, that is simply my f of x function divided by my g function, and it doesn't look like I can simplify. We need to make sure that our bottom function does not equal 0. So when I look at 2x minus 1, where can x not be? So I can solve for x. So 2x cannot equal 1, therefore x cannot equal 1/2. If we were to substitute 1/2 into x, 2 times half is 1, 1 minus 1 is 0, we're going to run into trouble. Our numerator, we know, has to be greater than or equal to negative 3. We knew that from the previous one. So where do all of these overlap? Well, earlier, otherwise the denominator of here can be from negative infinity all the way to half. Union, jump over half, and we can continue on to positive infinity. So where do all of these overlap? They're going to overlap at, we're going to start at negative 3. We're going to go all the way to positive half, jump over positive half because that's an asymptote, and we'll go to positive infinity. We also see that in the graph itself. I graphed it exactly as I have listed on the left. I see that x equals positive half here is an asymptote that I'm jumping over. I see that my graph is starting as far left as negative 3, which is included. And I am jumping and starting at negative 3, going all the way to positive half, jumping over half, and then continuing on to positive infinity. So now let's actually evaluate f divided by g of 1. Still, wherever I see x, I'm going to replace it with 1. The square root of 1 plus 3 over 2 times 1 minus 1. Square roots of 4 over 1, which is 2. So definitely take your time with these. Utilize Desmos to help you insert what is the arithmetic that function arithmetic operation that you're doing, so that you can definitely match the domain with the graph that you're seeing, which will be very helpful for you. The last topic we need to cover is the difference quotient. The difference quotient tells us that we need to take f of x plus h and subtract the function itself and divide it by h. Its geometric meaning is the difference quotient is the slope of our secant line. And in my picture here, if I've got 2 different points and I want to connect them with a line, this is the secant line. This will come in handy when you're if anybody's going to take pre-calc or calculus. There's a different way we can do this outside of algebraically, but for now we can do it algebraically. So we're trying to find what is the slope of this curved line when we set it at 2 different points. So if my points were here and here, the slope of this secant line would be very different than the slope of these 2 points. And we need a way to be able to find that, and that's where the difference quotient comes in. It's asking us to find and simplify the difference quotient for negative 3x plus 5. So there's three things that we need. We need to find what is f of x plus h, what is the function, and then divide that all by h and simplify. Well, to start off, let's find what is our function itself. That is negative 3x plus 5. So we've found this portion up here. Now we need to evaluate our function at f of x plus h. So wherever I see x, I'm going to substitute it with x plus h. Negative 3 times x plus h plus 5. I can also simplify this. This gives me negative 3x minus 3h plus 5. So I can distribute to eliminate the parentheses. Now let's actually plug that into the difference quotient, and I'll do that up here. We'll start off by taking the f of x plus h function, which we found here, negative 3x minus 3h plus 5, and I'm going to subtract the f of x function itself. We know that's here, so I'm going to subtract negative 3x plus 5. Notice I put it in parentheses because I'm going to subtract everything with my f of x function. Everything is being subtracted, and I'm going to divide that all by h. Now we can simplify. I can drop the parentheses on the left, distribute the negative. This then gives me positive 3x minus 15 all over h. Combine like terms, not 15, I'm sorry, negative 5. For some reason I was multiplying. Combining like terms, I have a negative 3x, positive 3x, positive 5, negative 5. I now have negative 3h over h left, which I can also eliminate because they are common factors in the numerator and denominator, which gives me negative 3. You can always expect that there will be something that will be crossed out in the numerator as you combine pieces together. It should be an expectation. All right, let's find the difference quotient of the function x minus x squared. So we need to know what is our f of x function, which is given. I need to know what is f of x plus h. So wherever I see x, I'm going to replace it with x plus h. And I'm going to have to do a little bit of simplifying here. So what is x plus h squared? X plus h squared is x plus h times itself. And then reducing it, or distributing, I'll have x squared plus xh plus xh plus h squared. Combining like terms, I'll have x squared plus 2xh plus h squared. Now I'll have x plus h minus what I just found, x squared plus 2xh plus h squared, which I can simplify one more time by dropping our parentheses and distributing the negative. And seeing if I can combine like terms, which I cannot. But f of x plus h is in fact all of this stuff. So it will take a little bit of extra work on the side if you have any quadratics that we are working with. The next part is to do the difference quotient then, because we have everything we need. We first need f of x plus h, which we just found to be x plus h minus x squared minus 2xh minus h squared. I need to subtract my f of x function, so I'm going to subtract everything. X minus x squared all over h. Now I'll release my parentheses and distribute so I can combine like terms in my numerator. X plus h minus x squared minus 2xh minus h squared minus x plus x squared all over h. It looks like I have a positive x and a negative x. I have a negative x squared and a positive x squared. So then what I'm left with is h minus 2xh minus h squared all over h. I see in my numerator that I have a common factor of h in each one of my terms. I'll factor that h out, which leaves me with 1 minus 2x minus h over h. So I now can eliminate the common factor in the numerator and denominator, leaving me with the difference quotient of 1 minus 2x minus h. So sometimes it can be a single number like the last example. Usually when we have quadratics such as this, you might have an h somewhere located in the difference quotient itself. And that takes care of lesson 1.5. In lesson 1.6, we will talk more formally about the fundamental graphing principle for functions themselves as we dive deeper into properties of graphs such as increasing, decreasing, as well as looking more at domain and range.